Some of you are probably right, this is a bundle. But also, a lot of you are thinking that this is painful because we, as front-end developers, strive to reduce the bundle all the time, reduce the bundle size. We spend a lot of time and effort on it. Our story is about a super tool we used to reduce the bundle size. And it took us from here to there without changing one line of code. What if you too could have a super tool that will automatically remove 4,250 import statements while improving your performance by 16% more than Terzer's tree shaking, which is considered the top of the top for bundle optimization. And it will reduce 14 megabytes of your bundle size, which is really a lot. Hi, I'm Omri Lavi. I'm a tech lead at Monday's DevTools group for the last 2.5 years. This means I'm building tools for developers so they can work with high velocity and with high confidence. I'm also part of the Foundations group, so this means I have opportunities to work on some really unique things, like the one you hear about today. So at Monday.com, we have a large and complex client code. We have more than 300 developers changing the client code on a daily basis. And we have millions of users, so each kilobyte we save from a bundle means a lot. This is why we look for innovative ways to reduce the bundle size as much as possible. And a while ago, we noticed the following pattern. We saw we had a lot of files that looked like this. They exported nested objects that, in the end of the day, only contained string values. This is why we call them constants files. And these files were being imported by other files that only used one or two of these values. And some of you are thinking, well, I have tree shaking for this. And for those who don't know what tree shaking is, if they haven't been on Asaf's talk, then tree shaking is a very common algorithm that most modern bundlers have today that allow you to keep in your bundle exactly what you're using while discarding what you're not using. But since we used nested objects, this didn't work for us. Tree shaking didn't work. So we ended up with having the entire constants files inside our bundle, which is what we see here. The red parts are actually the constants files. And this was a big deal for us, because we had many constants files. And this means we had more JavaScript that we ship over the network, so it took longer to download our application. And lastly, these files kept in the memory because they were never being cleaned up. And it felt a bit like this. We had a small piece of code that carried a huge luggage with it. So we had a dream. We wanted that while we're building the application, we'll detect these scenarios, and we'll calculate the exact values that are being used, and then we can remove the reference to these values, and inline the values inside our bundle. Then we can remove the import of the constants files, and we overall can remove the entire constants files and end up exactly with the values that we use. So we understood what we wanted to do, but we weren't sure how to do it. We knew we wanted to avoid major refactors because we had a lot of code. And also, we didn't want to do it manually because, again, we would probably do something wrong. So we wanted to do it programmatically. So after some thinking, we realized that the right thing for us would be to use ASTs. So raise your hand, please, if you know what AST is. OK, and keep your hand up if you ever used AST. So the truth is that we all use AST. We just may not know it, and we'll see it in a second. So AST, for those who don't know, is abstract syntax tree. It's a data structure used to represent a piece of code. And the best way to understand it is by a tool called AST Explorer. It's a free online tool. You can put code in it, like this one here. And then it will automatically show the AST of it. And it may be scary on the first glance, and it is. This is where AST Explorer helps you. You can select a piece of code, and then you can see its matching node. So in this case, it's the string ReactNext that has the node string literal with the value of ReactNext. You can also select this part to see it's actually a variable declaration node with the ID high, the value of ReactNext. And we can also see that its kind is a const. So now we understand what AST is, and we know how to investigate it using AST Explorer. And it's important to understand that AST is really everywhere. There are many, many tools that use AST. If you can think of ESLint or PostCSS, Prettier, Webpack, or really any bundler out there. And they all use AST to read and transform code programmatically. And it's the best way to understand how they use it is by an example. So let's see, for example, how Prettier is working. Prettier knows how to take this piece of code. Notice that it has single quotes. And when you save the file, Prettier runs on it and changes it to be like this. And notice that it has double quotes. And what it's doing behind the scenes is that it checks that if we see a string node with the quote type of single, then we set it to be with the quote type of double. And this part here is actually AST code. And this is the magic, the engine that runs Prettier behind the scenes. So we knew we needed ASTs, but how are we going to use it? On which framework? So we needed something that will allow us to manipulate code programmatically with ASTs. We needed it to be popular, so we can rely on its documentation and its community. We also needed it to be flexible for exactly our requirements. And lastly, we wanted it to be pluggable, so we'll be able to use it anywhere in our code. So we chose Babel for this, that has all of these features. And you may be familiar with it from your Webpack configuration, where it's very popular. So let's talk for a moment about Babel. How does it work? So Babel knows how to read your code, then parse it to have an AST. And then it runs plugins to generate new AST. And this is where you can step in and write your own plugin and that goes over all of the nodes of the AST and changes it as you find fit by adding nodes, removing, or mutating them. Then Babel knows how to take this new AST and generate new code of it. And this is how Babel is, generally speaking, this is how it works. So now let's get back to our original problem. After some work, we had the following Babel plugin that worked like this. We went through all of the references in our code. Then we detected those that are coming from constants files. Then we calculated the exact values that are being referenced and removed the references to these values and replaced them with the actual values. Then we could remove the import to the constant files and the constant files themselves. And we ended up with exactly the values that we needed. And a nice small piece of code. And some of you may be thinking, well, what could possibly go wrong with such implementation? So as it turns out, and how we learned, that a lot of things may go wrong. Because super tools come with super bugs. And the reason for this is that your regular code has user input as an input. Then you run on it some business logic to end up with some output. But in the case of AST code, we don't have user input. We instead have code input. And code is much more difficult to work with because it's less structured and there are many edge cases. And in a way, it reminds working with regexes. And for those of you who've ever worked with regexes know what I mean, because even a simple case becomes very complicated and there are tons of edge cases and you need to learn how to work with it. So with time, we learned how to work with ASTs and we defined to ourselves the best practices to work with ASTs. And this is what we wanted to share with you today. So we had many, many tips we wanted to share with you, but we have very little time now. So we'll focus on two things. The first is to write exec tests, and the second is to guard your assumptions. So we all agree that we should write tests. I hope we all agree. But we should also think about which types of tests we should write, because writing just unit tests is not enough. We need to have at least integration tests, so we know that all parts are working together and not that each part is working on its own. So this is how we came to learn, we need integration tests, but for AST tooling, which has specific requirements. So this is how we came to learn about exec tests that look like this. And it may be scary, but when you look again, you see it looks just like a unit test. It has the it part on the top, it has some input, then you're doing something in the middle, you're running something to get the result, and then you're making assertions on the result. But the input itself is actually code. And what you do with it is that you transpile it, transform it using Babel with your plugin to get the transformed code. And then, this is the magic part, we run the transformed code to get its output. And then you're making assertions, you're running assertions on the output. So you know that your plugin didn't introduce any new errors or new bugs. And you know that your plugin is working as it should. So exec tests are truly a wonderful tool, and they're very, very powerful, and they saved us a lot of time, and they found many bugs for our code. So exec tests keep you safe for all the known cases. But what about the unknown cases? So when you're developing AST tools, you can take nothing for granted, even if you're working with AST Explorer, as I showed you before, because you're guaranteed to meet new JavaScript features, which may be exciting if you're thinking of it, but it's less exciting if it's due to a bug in production. So what you should do is you should guard your assumptions. Let's say the best way to understand this is by an example. We wanted to show you an example from our code, but it was a bit too complicated for this talk. So let's talk about something simpler. Let's say I want to list out all the function names in my code. So a simple implementation would be to go over all function nodes and to print out the name property. And it should look something like this. We have the function node, we access its name and its value, and then we log it. And we're thinking to ourselves, it should be OK. But frankly, I had an assumption here, that all functions have names. And I should always question these assumptions. Because when you're thinking about it, it's quite common for function to have missing name, especially if you're working with React and you have many arrow functions that you use in useMemo or use callback. So in these cases, I'd like to have nice arrows during the build time instead of runtime. I'd like to have something like this that shows me exactly what went wrong and where. And the way you should do it is by guarding your assumptions. So generally speaking, it will look something like this. If I'm seeing a function node that doesn't have a name, then throw an arrow. But I don't want just any arrow. I want something specific that shows me all the details that I need. So in the case of Babel, it's by using a build called frame arrow, which creates an arrow with all the context that you need. And it may be annoying to get this error during the build, but it's much better than a bug in production. It also follows the fail fast principle, which says you should fail as soon as possible instead of later on. And lastly, it allows an incremental approach, so you can add more and more layers for your solutions as you find out about them. So remember, when uncertain, just throw. This will allow you to have a healthy development lifecycle. And this is the important slide, so be with me, because it summarizes all of these principles. So you start by implementing your solution. You list down all the cases you can think of, and you just go ahead and implement them. Then you guard your assumptions by adding sorry, I lost my attention for a moment. By adding assertions on the code itself, so you'll know about the cases you don't handle, and you'll have nice errors. Then you run your plugin, you run your tool, to find out all the cases that you didn't take care of. So you'll have these nice errors. Then you can investigate these errors using AST Explorer. And you can, once you know how to reproduce them, you can write exec tests for them, like the one I showed you before. And then you know that once you implement your new solution, you cover the cases that you didn't cover before because you have exec tests. And by following these principles, we could develop powerful AST tools that gave super impact. But most importantly, we learned a new thing. And now we have a super tool in our belt, and so do you. So our key takeaways is that ASTs are a superpower. And when you're meeting an impossible challenge, please think about AST as one of your tools in your belt. And lastly, when you develop an AST tool, use the AST dev lifecycle to maximize your impact. One last thing is that we're hiring, so if you're quick, scan this QR code. Otherwise, visit our booth outside. Thank you.